Welcome to The Explainer. Today, we are heading way out into the open ocean. We're going to tackle a massive engineering challenge and, believe me, an incredibly cool and elegant solution. So let me just ask you this. How do you stop something the size of a skyscraper from wobbling around in the middle of the ocean? Seriously, picture it. A wind turbine taller than a 50-story building, floating miles from shore, getting battered by wind and waves. How on earth do you keep that thing stable? To even begin to answer that, we first have to get our heads around the sheer scale of the problem. This isn't just a little boat rocking back and forth. This is instability on a completely different level. What we're talking about is a floating offshore wind turbine, or FOWT. And the whole idea is to get these giant machines into really deep water, because that's where the winds are the most powerful and the most consistent. But here's the catch. You're putting this enormous, top-heavy structure on a platform that floats. That creates a massive, fundamental problem with stability. Every single gust of wind, every wave that rolls by is trying to push this thing over. It causes the whole turbine to oscillate, to wobble back and forth. And that wobbling isn't just inefficient. A swaying turbine can't capture energy properly. It puts a huge amount of stress on the entire structure. That means more wear and tear and a much, much shorter lifespan. So how do you fix a problem that big? You can't just use a bigger anchor. The forces are just too immense. The real answer, it turns out, is to fight the wobble from the inside out, using something that's actually surprisingly simple, a giant, clever counterweight.
It's called a tuned mass damper, or TMD for short. And this isn't just any old chunk of metal. For this specific turbine, we're talking about a precisely engineered mass of 20,000 kilograms. Yeah, that's 20 metric tons, all designed to perfectly counteract the turbine's every move. But how does it work? Well, it's all in the name. It's tuned. By perfectly calculating the damper's mass, its springiness, and its shock-absorbing properties, engineers create a system that moves perfectly out of sync with the turbine's sway. The best analogy is this. Imagine you're carrying a full cup of coffee. As the coffee sloshes, you just naturally move your arm to cancel it out, right? A TMD is basically a giant automated arm for the wind turbine doing that exact same thing.
Now, obviously, you don't just build a multi-million-dollar turbine, stick a 20-ton weight inside, and just hope for the best. No. You test it. You test it over and over again in a virtual world first. So let's peek inside the digital experiment that proves this whole thing works. Engineers do this by creating what's called a digital twin. It's a perfect mathematical copy of the real turbine. In fact, the code used to run one of these simulations is the source material for this whole explainer. It lets engineers test every possible scenario with incredible precision before a single piece of steel is ever cut.
The simulation basically happens in 3 steps. First up, the engineers lay out the digital blueprint. They define every physical property, from its mass and inertia to how stiff it is. Second, they program the rules, the laws of physics and motion that the model has to follow. And finally, they hit go on the test. They simulate a big, sudden 10-degree push on the platform and just watch what happens for the next 150 seconds. Okay, this is the moment of truth. We've got the problem, we've got the solution, and we've run the virtual test. So now we get to see the results. Let's dig into the data and see what kind of a difference that 20-ton counterweight really makes. So the simulation was run 2 times. First without our tuned mass damper, and then a second time with it installed. We're about to see exactly how these 2 scenarios play out after that big 10-degree push. And honestly, the results are just staggering. Check this out. Without the TMD, the tower wobble is huge, and it's persistent. Even after the full 150-second test, it's still all over the place. But with our 20-ton counterweight, the peak wobble is way lower, and the whole system settles down in only about 50 seconds. This chart just makes the difference so clear. Without the TMD, the turbine is basically unstable for the entire test. With it, the system becomes stable more than 3 times faster. That's not just an improvement, that is a total game changer. And here's the kicker. The tuned mass damper doesn't just reduce the wobble, it absolutely crushes it. After that initial big push, the system with the TMD sees the tower's oscillation drop by more than 75%. That is an incredibly effective solution. So yeah, this is incredible from an engineering standpoint. But why should the rest of us care? Why is solving this wobble problem so important? Well, this goes way, way beyond just one turbine. The benefits here are huge. For starters, a stable turbine is a more efficient turbine. It generates more clean electricity. All that reduced stress means it has a longer lifespan with lower maintenance costs, making it more reliable. But maybe the most important thing is this. Solving the stability problem
unlocks the ability to build these things in really deep ocean water, and that lets us tap into the strongest, most consistent winds on the entire planet.
So, in the end, this isn't just about stopping a wobble. It's about how smart, focused, clever engineering is what makes the next generation of renewable energy a real possibility. This is how real progress happens, one elegant solution at a time. And that kind of leaves us with one final thought. The exact same principle, a tuned mass damper, is also used to keep skyscrapers from swaying and bridges from bouncing. It really makes you wonder, what other giant, complex problems out there are just waiting for an equally simple and clever solution?